So welcome to this video, which is going to be about isotopes and the periodic table. The first half is going to be about isotopes. The second half is going to be about the organization of the periodic table. So let me start the slideshow. Okay, so we have talked in class about the fact that we were talking about atomic theory in class, and we finished up by talking just really briefly about isotopes. Specifically, that one of the aspects of Dalton's theory, which proved not to be correct, is that all atoms of a particular element are identical. They are identical in the sense that they have the same number of protons. They must be, or they would not be atoms of the same element. But they can have different masses, and that's because they would have different numbers of neutrons, and that would make them isotopes. So isotopes are two atoms of the same element that have different masses because they have different numbers of neutrons. This is the table that was in the previous slide show. I just want to remind you about the various subatomic particles, particularly that protons and neutrons are both in the nucleus, and they're really the only particles that have meaningful mass. The electron has mass, but since it's about 1/2000th of the mass of either one of these other two things, it really doesn't count when we're talking about what the mass of an atom is. And so the nucleus essentially gives the atom all of its mass, and it is the protons and the neutrons that give the atom all of its mass, and they both essentially have equivalent masses. A proton and a neutron have, for our purposes, equivalent masses. Okay, so we're going to talk about what's called isotope notation, or formally is known as a nuclide notation. And it looks like, let me just click through to it looks like this, in which X is the atomic symbol of the element. So for example, if we were talking about carbon, X would be a C. If we were talking about fluorine, X would be an F. If we were talking about gold, X would be an AU. This symbol will then have in its upper left corner what's called a mass number. And the mass number is the mass of that atom. Remember, different isotopes have different masses. And so we're talking about a specific isotope here. That what we call the mass number A is the mass of the isotope. And then down in the lower left is the atomic number Z, which indicates the nuclear charge, or the number of protons. That also gives the atom its elemental identity. And so as we go through life, so in this presentation, this Z will appear down here, but as we get toward the end of the presentation, and as we go through this in sort of regular life, the Z kind of disappears. And the reason is because Z depends on the identity of Z is dependent on the identity of X. So if X is carbon, if X is a C, then Z has to be 6. If X is an O for oxygen, then Z has to be 8. If X is a U for uranium, then Z has to be 92. And so Z is kind of redundant, and so after a while, you're going to kind of see it disappear. So just to recall, as I was saying before on that table that gave the mass of all the subatomic particles, the mass number is going to be equal to the number of protons plus the number of neutrons, because they're the only things that have appreciable mass. And the atomic number is going to be equal to the number of protons in the nucleus, or the nuclear charge. So here's an example. Chlorine, what we would call chlorine 37. So the X is chlorine because it's chlorine. The Z, the nuclear charge, or the atomic number, is 17 because it has 17 protons in the nucleus. I don't like to beat a dead horse, but let me beat a dead horse. If this is Cl, this has to be 17. It cannot be anything else. If this is something other than 17, then this can't be Cl. But the mass can vary, and in this case, the mass of this atom is 37 atomic mass units. And so then how do we figure out how many neutrons there are? Well, if the mass is equal to the protons plus the neutrons, then we can simply manipulate that to say that the number of neutrons is equal to the mass minus the proton, or the number of neutrons is equal to mass minus the atomic number. And therefore 37 minus 17 is equal to 20. There's 17 protons and 20 neutrons. Again, neutrons is equal to mass minus the number of protons, or mass minus the atomic number, which gives. So here's a little opportunity for you to pause the slide, pause the video, I'm sorry, take a look at the slide and try and figure out how many protons and neutrons there are in each of these atoms. So you can go ahead and pause it and then write that down. And then when you're through, turn it back on and I will give you the answer. Right, so here are the answers, and you will notice that in every case, protons and the atomic number or the nuclear charge are identical. 8, 8, 16, 16, 47, 47, 82, 82, 35, 35. The number of neutrons is simply going to be the difference between these two numbers. It's the mass minus the nuclear charge, or the protons plus neutrons minus protons gives you a neutron. 16 minus 8 is 8. 32 minus 16 is 16. 107 minus 47 is 60. 81 minus 35 is 46. 207 minus 82 is 125. So that's how you do those proton-neutron calculations. Now, a nuclide symbol or an isotope symbol may also indicate a charge. Now, the number of electrons in an atom, in a neutral atom, is going to be equal to the number of protons, but they don't have to be equal. You can have an atom that has fewer electrons than protons, and you can have an atom that has more electrons than protons. And when they are not, and when those two things are not equal, then we indicate the difference by showing the charge in the upper right-hand corner. So this oxygen atom, we're saying, has a charge of -2. Because electrons are negatively charged, that means it has 2 extra electrons. Oxygen is element 8. You'll notice there isn't an 8 down there because, like I said, if it's oxygen, it must be that the atomic number is 8. Therefore, it has 8 protons. If it has a charge of -2, that means it has 2 extra electrons. Therefore, there need to be 10 total electrons in that atom. So let's try practicing. Let's go back to the same group of atoms that we were talking about earlier, but now charges have been indicated. There's a minus, and if there's no number, that just means it's 1. That means -1. That means -1. That means +1. If the charge is anything other than 1, then the number will be there. This means -2. This means +4. So it's not asking you here for protons and neutrons. It's asking you for electrons. So go ahead and pause the video, write down some answers, and then turn it back on. Okay, here come the answers. This atom has 9 electrons. It's got an extra electron because it's a charge of -1. It's got 8 protons, therefore 9 electrons. This atom has 18 electrons. It's got 16 protons. This symbol tells you it has 2 extra electrons because it's -2. Therefore, it's got 18 electrons. This silver atom has 46 electrons. The +1 means it's had an electron taken away because electrons are negatively charged. So it is 47 minus the one that was taken away, gives you 46. Bromine has an extra, bromine -1 has an extra electron. Therefore, it's 35 plus 1 is 36. Lead has had lead 4+ has had 4 electrons removed in order to give it a charge of +4. Therefore, it's 82 minus 4, 78 electrons. The worksheet that we're going to do for homework goes through all of this, and I'll do a couple sample examples for you at the end of the video. The periodic table, I gave you a copy of a periodic table in class for you to own and have and treat as your special thing. Let's just talk really quickly about how it was developed. The first periodic table was assembled by a Russian chemist in the in the 19th century named Dmitry Mendeleev, and he organized the elements by increasing atomic mass. And there were only 70 elements known at the time, not 118, and there were holes in his. Some of the elements that weren't known were actually right in the middle of the periodic table. He was sharp enough to figure out that things with similar properties kind of belonged above and below each other in the periodic table. So he actually left some gaps in his periodic table. But this is a really, really early version of it. It's a better, but that doesn't really look much like a sort of periodic table that we're used to seeing. And so if you take that and organize it in the way that we do, you will see that he came up with 8 groups, which is very similar to our modern periodic table. It has what are called 8 main groups. And you'll notice that he put things fell into the same group as they do on our periodic table. Hydrogen, lithium, sodium, potassium, rubidium, cesium were in his group 1. They're also in our group 1. Beryllium, magnesium, calcium, strontium, barium were in his group 2. They're in our group 2. So he grouped things together. He grouped things in terms of ascending mass, but he also he organized things by ascending mass, but he also grouped things together that had similar properties. His group 3 has boron and aluminum, like our group 3. His group 4, like our group 4A, has carbon and silicon, etc. And so that was his early periodic table. Now, Henry Moseley made one small change that he realized that the organizing principle of a periodic table shouldn't be increasing atomic mass, it should be increasing atomic number. And now those two things track very, very closely with each other, but not always. And so the proper way to organize the periodic table, the proper organizing principle is not ascending atomic mass, it's ascending atomic number. And that gave us the periodic table we have today. Here is a view of the one that I handed out in class. This is the periodic table that you can use for your own reference while you're doing homework at home. I've got laminated copies of this one to use in class on tests if you want. We obviously also have them hanging on the walls. You will notice that it's organized in terms of ascending atomic number. The number up here is the atomic number, 1, 2, and then a carriage return, 3, 4, 5, 6, 7, 8, 9, 10, and a carriage return. A little bit later in the chapter, in the unit, we'll talk about why things in the same group have the same properties. And groups are these vertical columns, if you think about this as a sort of spreadsheet. Okay. Groups 1 and 2 are part of what are called the main groups, and then groups 3A through 8A or 13 through 18 are also main group elements. You'll see it says that up here. So the main groups are 1, 2, and 13 through 18, or 1A, 2A, 3A, 4A, etc. These elements in the middle are called the transition metals, and they are all metallic elements. We'll talk a little bit about them later. Then you have what are called the inner transition metals, or lanthanides and actinides. They actually belong. You'll notice that here you go from barium to lutetium. There's a gap from 56 to 71. That's because this row of elements actually all belongs in this little spot right here. Similarly, there's a gap between element 88 and 103, and that's where all these elements go in. Why do we break this out? Why do we break these out and show them down here? It's not for any scientific reason. It's just so that they'll fit on a single page. If we showed the periodic table in the way that it actually ought to be depicted, it would look like this. And now there is no gap between 56 and 71. I've just put all those elements in there. There is no gap between 88 and 103. All those elements have put in there. But it's hard to get that on a sheet of paper and make it big enough for you to be able to see what's in the boxes. And so we depict it this way instead. But there's no magical reason for this. It's just to make it so you can see it. Okay, a little bit more about the periodic table. I mentioned this earlier, but let me go back to the periodic. The rows are called periods. So hydrogen and helium are in period 1. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon are in period 2, etc. The columns are called groups. So hydrogen, lithium, sodium, potassium, rubidium are part of group 1. Beryllium, magnesium, calcium, strontium, barium, part of group 2, etc. Fluorine, chlorine, bromine, and iodine are all part of group 17 or 7A. The vertical columns are called groups. Periods are called rows, groups are the vertical columns. There are two different numbering systems. I very much prefer the A, B system. And so I tend to talk about the main groups being groups 1 through 8, not being groups 1, 2, and then 13 through 18. And I'll explain the reason why to you later in this unit. So I prefer the A group numbering system, 1, 2, 3, 4, 5, 6, 7, 8. But I will sometimes refer to these as groups 13, 14, 15, 16, 17, 18, just to make sure that it's not ambiguous. And elements in the same group have very similar properties, as we will learn. There are 3 broad classes of types of elements, and those are metals, nonmetals, and metalloids. Metals are very much similar in a lot of their properties. They have high electrical conductivity. They're very lustrous. That is shiny. They can be drawn into wires. They can be hammered. They all are fairly similar in their properties. The nonmetals are all very different from each other. What they share in common is that they don't have any of the properties of the metals. So they can be gases, they can be solids, they can be liquids, but they generally do not conduct electricity and they are not lustrous. And then metalloids kind of have intermediate properties. And they are along what's called the stair step of the periodic table. So please pardon me for going backwards again, but the stair step is right here. This sort of stair step line. And you can see on this periodic table, the metalloids are actually kind of a grayish color rather than the white of the metals and the nonmetals. So the grayish color here is meant to indicate that these are metalloids. Okay. Metals. So now here we're going to talk about that certain groups have special names. And so group 1 of the periodic table, which is also known as group 1A, is called the alkali metals. So that would be lithium, sodium, potassium, cesium, rubidium. They react very violently with water. Group 2, beryllium, magnesium, calcium, strontium, barium. They're called the alkaline earth metals. Metals that are not in the groups 1 and 2 or not in the A groups are called transition metals. And then the ones I said that are broken out are called the intertransition metals. So here we go backwards again. Main group metals in groups 1 and 2, also in group 3. Transition metals here in groups 3 through 12 or 3B through 2B. Intertransition metals down here. There are also some special names for the non-metals, and there are 2 that you're going to have to learn. Group 17 or 7A, as I prefer to call it, are called the halogens. That would be fluorine, chlorine, bromine, and iodine. And group 18 or 8A, as I prefer to call it, would be the noble gases, which would be helium, neon, argon, krypton, radon, etc. Metalloids contain things like germanium and silicon and other things that are used in semiconductors and solar cells and things like that. So they're actually fairly important in our life and in our society. Okay, using your periodic table, I'm not going to go all the way back to the periodic table again, but using your periodic table or one that you have handy, try classifying each of these things as a metal, a metalloid, or a non-metal. You can turn this off for a second and then turn it back on after you turn it on. Okay, gold is pretty much right in the middle of the periodic table, so it's a metal, specifically a transition metal. Silicon, being on the stair step, is a metalloid. Manganese, careful not to confuse it with magnesium. Manganese is a transition metal. It's right in the middle of the periodic table in period 4. Sulfur is a non-metal. It's on the right-hand side. And then barium, which is on the far left-hand side toward the bottom in group 2, is a metal. What is the period? This is our last slide, I think. What is the period 3 element in group 2? So you're going to go down to period 3, which is the third row of the table. You're going to go across to group 2 or group 2A, and you will find magnesium. The group 7A element in period 4, so you're going to go down to period 4 or row 4. You're going to go all the way across to group 17 or 7A. Look for the elements there that is there. That is going to be bromine or Br. The noble gas in period 3, you're going to go down to period 3, which is the third row. You are going to go straight across all the way to group 18 or 8A, which is the noble gases, and you're going to find argon. All right, that's the end of the slides. You're going to have a handout, a homework assignment to do. And this is on either taking a isotope symbol and figuring out its atomic number, mass number, number of protons, electrons, and neutrons, etc. From that, or going in reverse. And so I'm going to do 2 examples for you. So let's fill in the blanks for this top one, which gives you 55 Mn. Now you'll notice that there is no atomic number here. Like I said, as we go further into this, we tend to ditch the atomic numbers and just go with the mass number. But this is manganese. Manganese, if we look on our periodic table, Mn is right here. It is element 25. So its atomic number is 25. Okay, remember this is the mass number, the 55. So I'm simply going to transfer the 55 there. How many protons? Well, we have said that the number of protons is equivalent to the atomic number always. So that is 25 protons. How many electrons? There's no charge indicated here, and it says here that the charge is 0, and therefore the number of electrons is going to be equal to the number of protons. If there is no difference, there is no charge. How about the number of neutrons? Well, we said that the mass number is equal to the number of protons plus the number of neutrons. Therefore, the number of neutrons is equal to the mass number minus the number of protons, or the mass number minus the atomic number. That's going to give us 30 neutrons. And we would call this manganese 55. That is its name. Let's go down and do this one in which you're given some information, but you are not given the name of the element or its mass number or its charge. We know that it has 47 protons, and therefore it must have, its atomic number must be 47. If it's got 47 protons, its atomic number must be 47. Now we look at our periodic table. We look for element 47. It's kind of hard to see because this is small, but that is Ag, or silver. So element 47 is Ag. I want to know what the mass number is. Well, remember that mass is equal to protons plus neutrons. It tells us here there are 47 protons and 60 neutrons. Therefore, I just add those up. 47 protons plus neutrons equals mass number. So I'm going to put that in there, 107. And I'm also going to put it over here. 107. What about the charge? Well, is the number of protons and electrons the same? It isn't. There are 47 protons and 46 electrons. That means it has one fewer electron than protons. It has had an electron taken away. Electrons have negative charges, so if you take one electron away, your atom is going to have a charge of +1, which means that I need to go over here and put a plus to indicate that this silver atom has a charge of +1. And then I'm going to write in silver 107. Okay, well I think those two examples should give you all the tools you need to finish this worksheet. It will be due next week. Feel free to direct any questions you have to me, and thank you very much for watching.